Hello and welcome back to Machines, Languages and Computation. At the end of the last lecture, I set you a little exercise to try to prove a statement for me. So in this lecture, I'm going to show you how that proof can be constructed using a method known as direct proof. So this was the statement I left you thinking about. If A and B are both whole numbers that divide exactly by 2, then A plus B is also a whole number that divides exactly by 2. In other words, you add up two even numbers and you get another even number. And what I wanted you to do was try to sketch out a proof of that statement. So a proof is an argument. It's a bit like evidence that you might place in a court of law to show that something has to be the case. Now, in a court of law, we often present evidence. Evidence isn't good enough here. We need an absolutely watertight argument that shows that this must be the case. And I suggested that if you didn't know where to start with such a proof, you might try this out for some actual values of A and B. Say A is 42, B is 6. I add up 42 and 6 and I get 48. And that's also even. So it works for that case. Question is, does it work for all cases? Sometimes when you're staring at a statement that you think may be true, a good way to attack it is to try to find a case for which it isn't true. If you can't find one, then that may give you a clue as to how to do the proof. Now what you'll notice here, before I get onto the proof, is that this proof involves an infinite set of numbers. A and B can be chosen from an infinite set of even numbers. So the set of even numbers is 0, 2, 4, 6, 8. Also the negative integers, -2, -4, -6, -8. So this set with 0 in the middle expands out in both directions, all the way to infinity. So there is no biggest even number. You tell me the biggest even number, I'll add 2 to it and get an even bigger one. And there's no smallest even number either. If you tell me the smallest even number you know, well, I'll subtract 2 from it and I'll get an even smaller even number. So it ranges all the way from plus infinity to minus infinity. So how can I cope with these infinite sets? The way that I do it is that I don't name actual numbers. I use letters to stand for the two even numbers. I say, let A be an even number, for example. The advantage of doing that is that if my argument works using just those letters, then we know it will work for any two specific even numbers. In other words, if I say, here's an even number, here's another even number, I don't actually tell you what they are, but I use the properties of those numbers, and my argument works, then I know the proof works for any two specific even numbers. Now, when you're working with letters in proofs, you might think it's a bit like algebra. So simple algebra, you might say x plus 3 is equal to 5, and you have to find what value x has. In this case, x is 2. Don't think of the letters in a proof as being actual numbers like they are in algebra. Think of them as standing for any number that has that property. So when I say let A be an even number, I'm talking about any even number. Let's see the proof. So I'm going to start by naming my two even numbers. I'm going to call them A and B. I'm also going to give a name to the sum. I'm going to call that S. So if I take A and B and add them together, I get S. My job is to show that S has to be an even number if A and B are even numbers. Let's think about how we can do that. So the first thing I'll do is I'll set some new names. P is going to be A divided by 2 and Q is going to be B divided by 2. Now you might ask me, well, why did you do that? And the answer is it's going to be useful to us in the proof. I've actually tried this proof many different times and I've tried many steps along the way to the proof. Now the problem is some of them didn't work. And therefore, if it didn't work, then what I do is I do that and I start again. However, when I do actually get a proof that works, then what I do is I write down all the steps of it so that you can see what I've done. So in other words, this mystery step here where I divide A and B both by 2 and call them P and Q, it's not going to be the first step of every proof. It's not a method. It happens to be the first step of this proof, and it's the one that led me to my goal. It's a bit like being in a maze. You're at the beginning of the maze. There are many different steps that you can take. Some of them are going to lead you to the goal. It might be there's only one that leads you to the goal. The others will lead you to a dead end. This is the step that led me to my goal. So let's let P be A over 2 and Q be B over 2. What do I know about P and Q? Well, because A and B are both even numbers, P and Q are both going to be whole numbers. In other words, they'll both be integers. I know that because A and B are even. So I can now rewrite the sum in this form. S is equal to 2 times P plus 2 times Q. And what I do know is that P and Q here are both integers. They might be odd, they might be even, but they are whole numbers. I can guarantee that for you. Now, what you can see is that you have an expression, and according to the rules of maths, you're allowed to, quotes, take the 2 outside the brackets. In other words, you can rewrite this expression like this. S is equal to 2 times P plus Q. Now, we're nearly there now, and you can probably see that we're going to get to the proof that we need. When we add P and Q together, because they're both whole numbers, then the result must also be a whole number. Because P and Q are integers, P and Q is also an integer. Now what happens if you multiply an integer by 2, or any integer multiplied by 2 is always an even number. So S is 2 times an integer, and therefore it must be an even number. And then I complete my proof with this little symbol here, this little square at the end, and that means QED. It's also sometimes known as a tombstone, the tombstone of smugness, because I've proven this thing beyond any doubt whatsoever. This is now proven. It is true. I can now use this theorem in any future proofs. I can now rely on the fact that 2 even numbers added together always gives an even number. Now, that was a direct proof. In a direct proof, what we do is that we start with known facts and we combine, and those known facts are known as axioms. We use definitions, such as the definition of an even number. We can use earlier theorems, and we work forwards towards our goal. There's other forms of proof as well, and we're going to see these in the class. Proof by contradiction is a different way of doing it. What we do is that we take the statement and we assume the opposite. So we take the opposite of the statement. So in the case of the 2 even numbers, we would say that adding together 2 even numbers doesn't give an even number. So it's, in other words, we assume the opposite case. And then we show that if that were true, a logical contradiction would occur. So the statement must be true. So we flip the statement on its head, negate it, as we say, and we try to prove that. We show that proving that leads to nonsense, so therefore the original statement is true. And we'll see an example of that. Proof by induction, well, you might have encountered this before. Some people will have encountered it before, but we'll be going over it because it's very important in computer science. Proof by induction allows us to prove a statement is true for an infinite set where there is a natural first element of that infinite set. This is called the base case. And what we do is we prove that the base case is true. We just usually just plug in some numbers and show that it's true for the first case. And then we use an induction rule, and that gives us all of the other cases. Because the base case is true, and because of the induction rule being true, that means the first case implies the second case implies the third case, and so on and so forth. It's often called the domino proof. And we'll be seeing that one next week. Meanwhile, that's the end of the lecture for today. That's the end of this week's lectures. So next week, we're going to look at these forms of proof in more detail.